sometimes we know that the linear model that we've been playing around with here is just not actually quite appropriate. That the true regression model needs to be nonlinear. For instance, if you were looking at drag force, one aspect of drag force is that the force is equal to some sort of drag parameter times the velocity squared. And so our underlying theory suggests to us, and that theory really being born from other experimental studies and looking at data, that there's some other nonlinear relationship at work here. And so one way that you might then begin to work with this in what some people call an intrinsically linear fashion is to linearize our variable. And so, for instance, we could let x be the square of the velocity. And now if we come back and look at this linear model up here, that'll tend to be very useful to us to then come along and try to understand something about what the KD value ought to be, right? And looking at data and estimating that slope parameter as well, right? Another sort of intrinsically linear kind of situation is where we think that a variable y is equal to a constant e to a constant times e raised to the beta 1 times x, and then multiplied by the air term, right? Here again, this is really an intrinsically linear kind of function, because if we were to take the log of both sides, then we get the sum of all these terms. And once again, things show up in a fashion. This is just a new intercept value, a new kind of air term, and the log of our response. Okay, and we then, though, and this is going to be key, is that we're going to be making this best fit in a transform space. And what that ultimately means for us is that the resulting model is going to be best in the transform space, and it may or may not be best back in the original untransformed space. And that's an important aspect of that to always keep in mind when you do these sorts of things. Right? Another example here might be where we'd have y equal to beta naught plus beta 1 times 1 over x, where we believe there might be some asymptotic behavior at work or response. And so there we could let z equal 1 over x, and then obviously then we get the straightforward version of the linear model. So again, sort of really, even though this is a nonlinear expression, if we transform things, then we get the same kind of thing. And sometimes you can employ this in sort of twice the fashion, right? So for our final example here, y equal to 1 over exp of beta naught plus beta 1x plus our air term, right? So you could let y star response function be 1 over y, and then you could linearize again by taking the natural log, and so on and so forth. There you'd have natural log of y star would be equal to beta naught plus beta 1x plus our air term. So there's a lot of different ways that we can approach it, but I again come back and caution you that you've got to really be thinking about how you could potentially misuse and abuse this kind of setting. And that's the last little piece here that I want to talk about, is this misuse and abuse. And the first one being one we've just already done, that if done in the transform space, the fit is best used in the transform space and not back in the original space. Now, it may work out just fine, but you have to be wary that depending on just how much of the linearization and the intrinsic linearity that you do or don't have is going to influence whether or not how good that fit in the transform space is back in the other one. And small little changes in the parameters that we come up with can have a huge implication even in the fitted space. And depending on what our transformation was, small little changes going back in the inverse of the transformation may have huge implications back in the other one, and you have to keep track of that. In a more general kind of standpoint, and this is not just associated with transform variables now, that you need to also be thinking about be wary of extrapolation. We've mentioned this before. We're going to come back to it in more detail later when we start doing some hypothesis testing on our parameters, our estimators. The crucial key aspect of this is that, again, you can have small little changes that can have enormous implications when we start extrapolating. Some people say, well, never extrapolate. Well, that's just not practical, depending on what field you are in. In my field, in civil structural engineering, we are almost always extrapolating when we're talking about design work, and not from the quality control standpoint of producing a material, but rather in terms of having collected data about potential design loads and then extrapolating to get to the structural reliability level that we're trying to work with. And so extrapolation is just totally unavoidable, but we have to do it then with a lot of circumspection. The other aspect of that is you have to be careful of the interpretation of the model, and particularly in the direction of what I mean here of causality. Right, it's one thing to be able to statistically demonstrate that there's somehow a statistical relationship between two random variables, but that does not mean that there's a dependent relationship, a real functional one. And I would go back to and point out, for instance, our Ogden Valley aquifer data and this estimated recharge versus the measured discharge. And I'll tell you, when I first developed this data and began to process it, I did it without really thinking about it very carefully, and I had these two flip-flopped. And when I got into the regression stuff and I started thinking about explanatory variable, well, wait a minute, recharge happens when we have rainfall that then comes down over the watershed and then somehow percolates into our aquifer. It may happen over a number of years, and so there may be some sort of relationship between withdrawing and the recharge, but it makes a lot more sense to think about the recharge somehow being connected with the discharge, that the recharge causes the discharge to be able to be possible, right? That makes a lot more sense, but the discharge somehow explaining how much recharge there is from a natural events kind of standpoint doesn't make a lot of sense. Now, having said that, the thing is that when you come down and look at these, you could easily, I mean, especially this data, which is fairly linear in its trend, we can easily come up with a model where we swap those two, and you'll find that the R-squared value, the coefficient determination, is quite high, and numbers such as 0.8 are quite high. Anything really greater than 0.8, we say, oh, gee, there's a significant linear relationship between those two random variables. And, gee, that explains this. One explains what happens with the other. Well, maybe it might be only a one-way thing. Now, mathematically, we would say, in fact, it wouldn't matter. It'd be the same R-squared value, no matter which was X, which matter one was Y. What would change would be slightly this model right here. Right, the coefficients beta naught and beta 1, those parameters would change. So you have to be very careful on how you interpret these models and start thinking about the supposed causality issue. For years we were able to demonstrate that statistically there was some sort of significance between smoking and lung cancer. What we didn't have was a functional or a phenomenological model that explained exactly why smoking caused lung cancer and what that why it was in some people it happens and other people it doesn't, what the role of secondhand smoke is, and all those sorts of things are all factors that are hanging out there that made it difficult to convince some folks that there was an actual real functional relationship between those two. Our current culture says that yes, there absolutely is, and it sort of in some sense makes sense, but you can also see a point to be made in the other direction, right? It also becomes a political hot potato as well, I understand. Right? So there's a lot of things that we can do that are a misuse and abuse of this notion of a best fit line. And we have to be very careful of the interpretation of the model, this notion of causality. We need to be a high level of the coefficient of determination does not necessarily point to causality either. Okay.